we have is BRF5 polar or nonpolar? So let's first find out by actually getting the Lewis dot diagram of bromine pentafluoride. So the way we do that is by seeing how many electrons we're working with. So bromine and fluorine are both high halogens. So in a sense, we have 6 halogens total we're working with because 5 fluorines. So because there's 6 halogens, that's 6 times 7 electrons for each halogen. So in total, we're working with 42 electrons. So now because bromine is the only one that's bromine and the rest are all fluorines, we're going to put that in the middle. Okay? We're going to surround it by fluorines. 3, 4. I'm going to put the awkward one here, that 5th one. I'm going to just start adding the bonds. That's one bond there, one bond there, one bond here, here, and here. So that being said, right now, bromine, if we were to start there, is sharing 5 of its 7 electrons, based on the fact that it has to share 1 with each fluorine. Because its valence electrons are 7, it still needs 2 more, which I have now added. So this now would be the bromine molecule in the middle. And fluorine is actually sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7. And that's what's going to happen for each one. And you see that we've now satisfied the octet rule for everything but the bromine. The bromine breaks the octet rule because of the fact that it's bromine. You'll see some atoms in the periodic table break the octet rule. Usually it's the bigger ones. For example, like bromine, it's here breaking the octet rule, where instead of 8, it now has 12 electrons surrounding it. So, with that being said, let's now check out to make sure that we have the formal charge done correctly. Bromine in the middle, it's going to be 7 valence electrons, and it's going to be subtract. It has only 2 to itself, but it's sharing a whole 10. So that's 2 plus 5, that's 7. So perfect. And the fluorines are all the same. It has 6 to itself, and it's sharing 2. Perfect. Okay, so that is done correctly. This is indeed the Lewis structure for it. So now, to say whether it's polar or not, we can actually just say right away that it's not polar, but we have to make sure that we actually understand its molecular geometry. The reason why I say we can say that is because it has just one lone pair. Okay, and because that's one lone pair, that already offsets everything. There's literally a lone pair that's unaccounted for in the distribution of the atoms around the bromine. So there's something already off there. Okay, so with that being said, though, let's just go through and actually find the actual shape. So there's 6 things right now attached to the bromine. The reason why I say 6 is because there's 5 fluorines, yes, and 1 lone pair. So in total, that is 6. Alright? And that hybridization is sp3, because that's 4 right now, because s is 1, and then plus 3 p's, and then d2. That is a hybridization for that. Okay? And things that are hybridized like this have an electron geometry shape of octahedral. Now, that doesn't give us our answer just yet, actually. We have to now actually factor in what type of things are attached to it. So we do have 5 bonds, yes. But now, as we said, 1 lone pair. Okay? Because of that, the shape is known as square pyramidal. Alright? Where if you kind of just put the if you redo it, bromine, you put the lone pair at the bottom, alright, and then you kind of have a square that kind of looks like this on a plane. So the lone pair is kind of under the plane. You have all the fluorines right there, and the last fluorine sticks out above the plane. Because now, if we drew it like this, where we have the bromine, and we look solid 2D, this is what the plane would look like. These cancel out. The fluorine's on this side. But here's the issue here. The fluorine above and the bromine down here, I mean the lone pair, they're not the same thing. So there's already a difference in pull. So because of that, I'm going to say it's nonpolar. You can even look at the electronegativity difference. It's not that big. So in theory, they would be like, if it was just like a bromine, oh sorry, that's bromine chlorine. Bromine and fluorine, yes, that is a huge electronegativity difference. So because of that, they are all polar bonds, true. But now in order to see whether the whole molecule is polar or not, we have to see if all these polar bonds cancel each other out. And because of this lone pair, they don't. So knowing that, we can now say without a doubt that this is going to be a polar molecule, because our molecular geometry is square pyramidal, and as you can see here, it's not even distribution between the fluorine and that lone pair. Okay, so this is what we have. As I said, square pyramidal, which is what I drew, and therefore it's polar and has net dipole moment pointing towards this fluorine up here, because of the fact that it's a more electronegative between them, between bromine and fluorine. So now let's move on to question number 13.